Hello, and welcome to the BigML tutorial series. In this video, we will be discussing Flatline. In the introduction section, we will begin with a definition of what Flatline is and discuss how it enables feature engineering and programmatic filtering in the BigML platform. And while the concept of filtering is probably clear, feature engineering may be a new concept, and so we will define this as well and discuss why it is important. And then we will look at some examples of feature engineering and programmatic filtering which happen automatically in the BigML platform. In the basic section, we will explore the built-in functions available for feature engineering and filtering. And we will explain the options for refreshing the type and preferred status detection when creating new fields. In the advanced section, we will formally introduce Flatline Expressions, which enable the full capabilities of Flatline to perform complex feature creation using Lisp-style expressions. We will then go through several demos of creating custom transformations using these Flatline expressions. So what is Flatline? Flatline is a domain-specific language for feature engineering and programmatic filtering. There is a lot of information packed into that sentence, so let's break it up a bit. First, what is the significance of a DSL? Flatline was invented by BigML to fulfill the need to perform feature engineering and filtering in a programmable, repeatable way that is optimized for speed. Without Flatline, this critical aspect of machine learning would have to be done manually outside of the BigML platform. Within BigML, Flatline works with datasets, and after transforming them either by adding new fields or by filtering rows, it outputs the results in a new dataset. The transformations are written in a Lisp-style syntax that is part of the Flatline specification. We will see examples of this in the advanced section. It can be a little difficult to learn at first, but with practice it becomes quite natural and easy to use. Next, we have programmatic filtering. With Flatline, you can write expressions that operate on a dataset row as an input and evaluate it to true or false to decide whether or not to keep the row. The power of Flatline in this context is twofold. First, the filter rule becomes code that is easy to reuse, and second, Flatline is optimized to work quickly, even on large datasets. So what about feature engineering? What is that, and why is it important? Let's begin with the definition. While there is no universally accepted definition, a good one to understand the meaning is this. Feature engineering is the process of applying domain knowledge of the data to create new features that allow machine algorithms to work better or, and this is important, to work at all. And the dirty secret of machine learning is that feature engineering is really, really important. Spending a little time creating better features will generally improve a model more than trying different algorithms. But why? So the first thing to understand is that machine learning algorithms have no deeper understanding of data. If you provide a numerical field in your data, then the algorithm knows that they have a natural order, that they can be operated on mathematically, for example, to scale them, etc. But that's it. And if you provide a categorical field, then it knows that they are discrete values, nothing more. There is no sentience or experience over time being applied to your data. The algorithm only functions the way it was programmed. This is important because sometimes machine learning appears to be magical. But the magic that happens is the ability of the algorithm to find relevant patterns quickly and efficiently. But the algorithm only knows what you tell it or show it with data. So if you build a model to predict diabetes and the model discovers that the body mass index is important in predicting diabetes, this is because the data shows this relationship, not because the model understands what body mass index is. It has no idea. It's only a numeric value that correlates with the objective. In fact, in that same medical context, if you only provided the weight in kilograms and the height in meters, the model may discover a relationship between these measurements and diabetes. But when you provide the body mass index, which is the weight divided by the height squared, this is a better predictor and the overall quality of the model will improve. Knowing to use this ratio instead of the two individual fields is an example of applying domain knowledge to allow the machine learning system to work better. Another example, in a financial setting, you might have debt and income details for loan applications, but with knowledge of the lending space, you might suspect that combining these into a debt-to-income ratio is more predictive for loan risk. Now, of course, sometimes domain knowledge can be subject to speculation and bias, and relying on intuition can be risky. This is where your role as the domain expert complements the machine learning algorithm. After creating new features, the machine learning algorithm can test whether or not they perform better by using an evaluation. Now that we have a high-level understanding of feature engineering, let's take a look at a few ways in which BigML transforms your data automatically to make machine learning algorithms work better. The first is date-time fields. If you think about it, the way we specify timestamps is arbitrary. In fact, there are lots of different standards for how to display a date and time. The problem here, then, is that there is a lot of useful information packed into a date-time specification. By splitting out the relevant time components, say into the year, month, day of week, etc., as numeric and categorical values, the machine learning algorithm can now discover time-based patterns. And this transformation happens automatically when BigML detects a date-time field in your data. Another example of an automatic transformation is the handling of categorical fields for clustering and logistic regression. Both of these algorithms rely on mathematical computation. For clustering, it is a distance function, and for logistic regression, it is the logit function. These functions can only operate on numeric inputs, and so the categorical values have to be transformed to a numeric representation. This transformation happens automatically, which is why you can upload a dataset with mixed numeric and categorical values and press one-click cluster without having to worry about it. Another example of automatic transformations is the handling of text fields. Unstructured text contains a lot of potentially interesting patterns, but the incongruities of language make it difficult to extract. By performing a bag of word analysis, the text field becomes a vector of interesting tokens discovered in the text field, which makes it possible for the machine learning algorithm to find patterns relating to the occurrence of words. Note that another option for text fields is topic modeling, which produces a deeper thematic extraction from the text. Now, of course, these automatic transformations sometimes are not enough, which is when feature engineering becomes important. For example, what if a text field is not actually unstructured? This example comes from the StumbleUpon dataset. One of the fields in that dataset is called the boilerplate, which contains the text of the website that is being analyzed. However, this field is not just the raw text of the site, but rather a little JSON document with key value pairs that denote the URL, the title, and the body of the HTML page. In this case, this text field has a deeper structure. It is actually multiple text fields. By extracting these key value pairs as separate text fields, the machine learning algorithm may work better. Let's find out. So I have the StumbleUpon dataset with both the original boilerplate field, but also with extracted key value pairs as new fields. So we have both the boilerplate body and the boilerplate title. Since we want to know how this model will perform, we will begin with a training and test split. For the first model, we will configure the model, we'll select the objective as the label, and we'll remove the two new fields. And now that we have the model built, we'll run the evaluation. Now let's return to the dataset and build the model with the new fields included as well. We can see already that the splits are different in the tree, and in fact this tree has chosen the boilerplate body at the root of the tree. Let's evaluate this tree as well. And now let's put these evaluations side by side. As we can see from the overlaid ROC curves, the StumbleUpon model built with the new features has a slightly better area under the curve of 0.78 as opposed to 0.77. So we've got about a 1% bump in the AUC just by extracting the structure out of that text field. And so we saw in that demo that by engineering these new features that extract the structure from the boilerplate field, we can improve the model. So with feature engineering, we help machine learning algorithms to work better. But what about this idea that sometimes we need feature engineering to make machine learning work at all? Let's consider a data set of US highways where we have the highway number, a field that indicates the primary direction of that highway, either north, south, or east, west, and another field which indicates if each highway is long or not. What would happen if we use this data set to try to predict the principal direction of a highway based on the highway number and the length? Let's find out. Here we have the highway data set with the highway number, the direction, east, west, or north, south, and the is-long field, which is false or true. So let's build a model to predict the direction. In this tree, we can see that the model is using the highway number to split, and at a casual glance, this model seems fine. It will even evaluate reasonably well if we were to do a training and test split. But if we examine these branches, we can see what is happening. Basically, the model is splitting on the highway number over and over until it isolates a small enough subset of highways that it can finally say something about the direction. If you think about it, this is not interesting at all. The model is basically remembering the training values and is not gaining any insight about the relationship between the highway number and the principal direction. However, as it turns out, in the US highway system, there is a relationship. Even-numbered highways run east-west, and odd-numbered highways run north-south. But the model is not finding this pattern. Why? To understand why, remember that all the algorithm knows about the highway number is that it is an integer. That is, it has a natural order, it can be scaled, etc. It doesn't know anything about even and odd numbers, and so it cannot find that pattern. Let's return to the data set and engineer a feature which indicates even or oddness of the highway number. This will be a sneak peek at how to add a new computed field with a flatline expression, but we won't go into the specifics of this expression until the advanced section. We'll call this new field isEven. I'll choose the option here that's called a Lisp S expression, and this is the expression I'm going to use. Suffice to say that this expression is computing the highway number modulo 2 and comparing the result to 0. So if this new field is true, then the highway number is even. Otherwise, the highway number is odd. So here we have our new field isEven, false, or true. Let's retrain the model and see the result using this new field. Now we can see that the tree is significantly different, and in fact the model has discovered the very strong relationship between the highway direction and the even and oddness of the highway number. So in this case, isEven is false, meaning that the highway number is odd, and the model is predicting that that highway will have a principal direction of north-south, which is the pattern we expected it to find. Although this is the pattern we expected to find, remember that the algorithm still has no idea what the field isEven means. This is just another feature in the dataset which the model discovered has a strong correlation with the objective. So in the introduction, we saw a few ways in which BigML automatically transforms your data to help the machine learning algorithms work better. And then we ended with a few examples of how, by applying some domain knowledge, we can improve models with manually created features. In the advanced section, we will see how to perform these types of transformations explicitly with flatline expressions. However, BigML also provides several common functions for transforming and filtering your data that do not require knowing how to write these flatline expressions. Internally, these built-in filters write a flatline expression for you, which you can then examine if you like. The built-in functions available for filtering depend on the field type. First, for numeric fields, it is possible to filter by comparison, for example, a field being less than or greater than a specific value, or filtering by equality, for example, is a field equal to a specific value. It is also possible to filter on a numeric field by whether or not the values are missing or if they meet certain statistical criteria. In a similar manner, for datetime fields, it is possible to filter by comparison to a date range, equality with a specific date, or by fields that have a missing date time. For categorical fields, you can filter by matching a specific class or by missing values. And for text fields, it is possible to filter by whether the text field exactly equals a string, whether it contains or does not contain a string, or by if the text field has a missing value. One final option when filtering is the refresh fields option. The first is the types. When filtering a dataset, it is possible that the field type might change. For example, if a categorical field has more than 1,000 classes, then when you create the dataset, it will be forced to become a text field. After filtering, you may have fewer than 1,000 classes, in which case this field could become a categorical again, and enabling the refresh option for types will allow this to happen. In a similar way, you can force a refresh of the preferred status for each field. So let's see an example using the StumbleUpon dataset. We will create a filter which separates the rows that match the boilerplate containing the word cup. The alchemy category is not sports nor unknown, and the alchemy category score is greater than or equal to 0.7. Starting from the dataset view, we simply go to the gears icon and choose the option to filter the dataset. We can then begin building the filter rules. We want to filter on the boilerplate, and so the comparisons available for a text field are whether or not the text field is equal to a string, contains a string, or doesn't contain a string, or has missing values. In this case, we want to filter rows that contain, perhaps in a case-insensitive way, the word cup. We want an additional condition on the alchemy category, so we can just press the Add Condition button and select the alchemy category. In this case, since this is a categorical field, the options are to filter on specific classes or on whether or not there are missing values. For this example, we want to filter rows where the alchemy category is not sports, so we can select that class, and is also not unknown, and we can select that class as well. Now we had a third condition we would like to add, and so we add another condition, again with an and this time we're filtering on the alchemy category score. And since this is a numeric field, we have options to filter by comparison, whether or not the field is equal, whether or not the field has missing value, or whether or not the field matches certain statistics, like between percentiles or below or above a mean. In this case, we want to filter by values that are greater than or equal to 0.70. And so this set of rules matches the criteria we selected. Once this filter expression is created, we can press the Create Dataset button to output a new dataset that contains only the rows that match those criteria. We can see there are now only 42 rows, and if we look at the alchemy category, we don't expect to find sports or unknown here. Likewise, if we look at the alchemy category score, the lowest values start at 0.7 because we filtered for only rows that are greater than 0.70. So in the same way that there are built-in functions for filtering, there are also built-in functions for engineering new features. The first is Discretize. This converts a numeric value into a categorical, typically by sorting the values into percentiles. There is also a built-in function for replacing missing values. You can replace them with a fixed value, the maximum value, the mean, the median, etc. You can also normalize a numeric value, which changes the range without altering the distribution. This is something that clustering does by default when autoscaling. There are several built-in mathematic functions, for example, exponentiation, logarithms, squares, roots, etc. It is also possible to force a field type to become a categorical, integer, or real valued number. If you would like to introduce some noise into your dataset, this can be achieved with the random function. And there are several options for creating a new field based on the statistics of an existing field. And finally, we have the same options for forcing the refresh of field types and preferred status. Let's see an example of discretizing a numeric value. This is a particularly useful function when you have a numeric field you want to predict, but would prefer a classification model. This might be perhaps because you would rather be able to evaluate using the F measure instead of the R-squared error, etc. So in this example, we have some customer data, and for each customer we have the total amount that they have spent. If we build a model to predict the spend for new customers using this data, we are going to get predictions like this new customer will spend $3,521 with an expected error of 1,232. However, this numeric prediction of the amount a new customer might spend probably is not as useful as just knowing if this customer is likely to spend a lot or a little. Well, what do we mean by this? Well, instead of predicting the exact spend amount, what if we predict if the new customer will be in perhaps one of three classes: the top third, the middle third, or the bottom third of all of our spenders? This is something we can do with discretization. So let's see an example with this data taken directly from this slide. So from the Sources tab, I can create an inline source. And after clearing the editor, I can just paste that data directly in from the slide. And we'll call this spend data. So now we have the total spend. So let's go ahead and create a data set. So from the dataset view, we're going to choose Add Fields to Dataset. And since we're creating a new field, we can give it a name. In this case, we'll call it the spend level. And you can see that the default operation is to discretize by percentiles. But we can also see the other operations that are available by clicking on this menu. So we could replace missing values. We could do some normalization. We could compute some basic mathematic functions. We could do some typecasting. We could create a feature that had random data. We could create a new feature that was based on the statistics of an existing feature. Or we could create a new feature using these S expressions, which we're going to see in the advanced section. For this demonstration, we want to create a new feature that is discretized by percentiles. And so now we select the field that we want to discretize, which in this case is the total spend. And then we need to choose how many split points we want. So median will just give us 2 groups, terciles will give us 3, quartiles 4, quintiles 5, etc. Since we want to know the bottom, middle, and top third of our spenders, we'll select terciles. So with those options, once we hit Create Dataset, our total spend category will be discretized into a new feature called the spend level. And you can see that we have 2 customers that are in the first third, 1 customer that is in the second third, and 2 customers that are in the third third of the spend level. And this new field, as desired, is a categorical value. Now that we have seen some of the ways in which features can be created automatically or by using built-in functions, let's look under the hood and learn how to write flatline expressions. The first thing to know about flatline is that expressions are written using a Lisp-style syntax. If you don't know what that means, just remember that operators come first. So you would write +1, 2 to add 1 and 2, instead of 1 plus 2, which would be incorrect. Also, you will need to learn to be generous with the use of parentheses. Dataset fields are first-class citizens in Flatline. This means that when you want to include the value of a field in an expression, you can indicate this with the field operator. In this example, the value of the field diabetes pedigree in each row will be substituted in the expression. Flatline also has support for limited programming language structures, which makes it possible to create very complicated expressions. Flatline is not a Turing-complete language, however, so you will not be able to simulate any arbitrary algorithm. That said, it is still possible to use constructs like let, condition, if-then expressions, maps, list operators, and of course the various mathematical functions that you would expect. Note that this is not a complete list of all the functions available in Flatline. Additionally, there are lots of useful built-in transformations. These can be used to compute statistics, to deal with strings and regular expressions, to parse timestamps, and to even create expressions which rely on field values in other rows or columns using something called windows. It might be easiest to learn by example, so let's jump right in. In this data sample, we have the debt and income for several loan applicants. However, we have an intuition that the debt-to-income ratio will be more useful in predicting the credit risk, and so we would like to add this feature to our dataset. Again, we will use an inline source and just paste in those values directly from the slide. Once we've created the source, we'll go ahead and create a one-click dataset. From this dataset view, we can now add a field to the dataset. We will call the field DTI as an abbreviation for debt-to-income ratio. And instead of choosing one of the built-in operators, this time we will choose the Lisp S expression. We want to compute the debt divided by the income, so the operator is divide. And now we need to specify the numerator, which is the field debt. And this is followed by the denominator, which is the field income. Now we close the operator with a final parenthesis and hit Create Dataset. And now we have a new dataset with the debt-to-income ratio field added to it. We can also filter datasets using Flatline Expressions. Any Flatline expression that evaluates to true or false can be used to filter a dataset. When processing the dataset, each row will be passed to the Flatline expression. If the expression is true for the row, then the row will be kept in the output dataset. And if the expression is false for the row, then it will be discarded. Notice that filtering can be direct by specifying the S expression in the filtering menu option, or it can be done in two steps. That is, we could use the Add Field options to create a new feature, and then use one of the built-in functions to filter on this new feature, as we saw in the basic section. Let's return to the debt-to-income ratio data. For this example, we would like to filter the applicants so that we only have customers with a debt-to-income ratio of less than 35%. Now, we could take the dataset with the computed DTI field and use a built-in function to filter. But for this example, let's assume that we want to directly filter these applicants by DTI, but we don't need the DTI for the next step, and so there's no reason to compute it in a separate step. So we start with the same dataset as before, but rather than adding a field, we will choose the Filter Dataset option. In the field selector, if we scroll all the way down, we can see that there's an option to filter by S expression. Next, we can specify JSON format or Lisp format. The JSON formatted S expressions have the same functionality as the Lisp format, except that the string has to be a JSON list. The choice between them is purely aesthetic. For this video, we will stick with the Lisp format. In the last example, we computed the DTI with this expression, the field debt divided by the field income. But now we need this expression to evaluate to true or false to specify which rows to keep. We want to keep applicants with a DTI of less than 35%. So all we need to do is add a comparison operator, and then the value to compare it to, in this case 0.35. And now we can hit Create Dataset. In the output, we have now just the 3 applicants that meet this criteria of a debt-to-income ratio less than 0.35. Sometimes when working with unlabeled data, it is possible to add a label with a flatline expression. For example, here we have some loan payment data, but there is no label indicating which of these customers have defaulted on their loan or not. In this case, we could define default as meaning that the customer has missed 3 payments in a row. With this definition, we would see that only the second customer, Jane Plain, has missed 3 payments in a row and is therefore in default. Let's see how we could create this label with Flatline. Again, we'll create an inline source and just paste the data in directly from the slide. Now that we have the source created, we can go ahead and create a one-click dataset. Now we select the Add Fields to Dataset option, and we'll name this field Default. In the Operation window, we will again choose the Lisp S expression. So how are we actually going to compute this? One idea we could try would be to simply compute the sum of the last 3 payments. We would do this using the addition operator, and then we would just specify all 3 of the previous months. So we have month minus 3, and we would add to that the field month minus 2, and we would add to that the field month minus 1. Now with this expression, it certainly is true that if all 3 payments are 0, then this sum will be 0 as well. However, there could be a negative payment, and so it might be better to sum the absolute values of the payments. But what is the function for computing the absolute value? Is it ABS? Or perhaps it's the word absolute? Or maybe it's just a pair of pipe characters? To answer this, let's open the Flatline editor by clicking on the small pencil icon within the expression input box. This panel presents us with a preview of the input dataset and an input box with syntax highlighting for our Flatline expression. With our test expression here, we can press the Validate button, which will compile this expression and report any errors. In this case, we can see that the pipe character is definitely not correct. We'll remove them and try just typing ABS. As we type, we can see that the word ABS turns pink, and from the syntax highlighting, we understand that Flatline recognizes this as a valid operator. In fact, if we just type AB, we can press Control Space to bring up an autocomplete, where we can also see the function listed here. With the function selected, in the help panel below, we can see an explanation of this function, along with a summary of how to use it. Let's put ABS on all 3 of the month values and make sure we've got the right number of parentheses. Now we can press Validate and see if the expression is valid. Since the expression is valid, we can now press the Preview button, which will show us an example of applying this transformation to the sample data above. As we can see in the preview, this is not exactly what we wanted. We wanted a Boolean that is true when the last 3 months are all 0, and instead we have the sum. We can modify this expression with a condition that compares it to 0. Once again, we can press Validate, and since the expression is valid, we can press Preview. And now looking at the sample output, we can see that this is the field we want. Mary Happy is a default of false, Joe Schmo is a default of false, and Jane Plain, with 3 payments in a row of 0, has a default of true. Since this is the expression we want, we can click Accept, And now we can hit Create Dataset. And our output dataset now has the default label. So far, all of these examples have computed a new field based only on the values in a single row. But it is possible to write expressions which use other rows as inputs as well. As an example, let's compute the shock over a 4-day moving average for a daily stock price. For the first day, we have no previous prices, so we cannot compute a 4-day moving average. On the second day, we have a price from yesterday, but still no day minus 2, day minus 3, or day minus 4 prices. This continues until we get to day 5. We now have a complete set of 4 previous prices, and we can compute a 4-day average, which in this case is 316.25. And now we continue this for each subsequent day, computing the average of the last 4 days. In order to relate this moving average to the change that we expect in a current day, we will compute the difference between today's price and the 4-day average, and then scale it by the standard deviation. If this number is large, then this implies that today's price has moved more from the 4-day average than is normal. And if this number is small, then the change is equal to or less than the standard deviation, and so it's a normal day. This gives us a way to see if the stock price has changed an unusual amount on any given day, at least compared to the last 4 days. So how do we compute this expression in Flatline? First, the current price at any row is just the field price. For the 4-day average, Flatline has a function called average window, which can compute the average of any field over a specified window of rows relative to the current one. The first option to this function is the field we want to compute the average of, which in this case is again the price. The second input is the row to start from, which we have specified here as starting from -4, meaning 4 rows before the current row. And the third option is the last row to include in the average, which is -1, or the row immediately before the current row. Flatline also has a built-in standard deviation function that we can use directly. Let's try this in BigML. So once again, we'll create an inline source and paste in those stock prices directly from the slide. With the source created, we'll now do a one-click dataset. To compute the shock, we're going to add a field to the dataset. We'll call this new field the shock. The operation will be a Lisp expression. And now let's write the expression. So we want to take today's price, and from that, we want to subtract the 4-day moving average. Now we want to divide this result by the standard deviation of the price. We can do a quick check in the Flatline editor to make sure there are no typos. The expression looks valid, and if we do a preview, we can see the values are being computed. The first 4 have no value because there isn't enough data for a 4-day average, but now we're getting values that look correct for a shock value. We can accept this expression and create the data set. And now we have the desired shock value as a new feature in our data set. Now let's look at some more advanced expressions. Remember from the introduction section the highway transformation that we did. Now we can understand how it works. Starting from the innermost set of parentheses, we take the highway number, then divide it modulo 2, and compare the remainder against 0. If the remainder is 0, then 2 divides the highway number and it is even, and the expression will be true. If the remainder is not 0, then it must be 1, which means that the highway number is odd, and the expression will be false. Flatline can transform date times as well. Here's an expression which transforms a timestamp into the phase of the moon as a percentage of the lunar cycle. 0% means the moon is new, 25% is the first quarter, 50% is full, 75% is third quarter, and 100% is a new moon again. This works by computing the epoch of the date time field, which is the number of seconds since January 1st of 1970. The phase of the moon is known at that date, and so this basically just computes a large modular arithmetic based on the number of seconds since that date. Sometimes flatline expressions can become quite complex. Here's an expression which computes the distance on the surface of the Earth between a latitude and longitude pair and a reference point based on an approximation of the Haversine formula. Obviously, this expression is quite unwieldy to cut and paste into the flatline editor. Fortunately, there is a solution. Although Flatline only operates on datasets, WisML, BigML's domain-specific language for workflow automation, can perform any complex task within BigML, including applying flatline transformations. So we have our flatline expression which computes the Haversine, and we can wrap this in a WisML script. This allows us to define the inputs, which consist of the latitude and longitude reference point coordinates and a dataset to transform. And we can also define the output as a dataset. And now that we have a WisML script which wraps this flatline expression, we can share it in the gallery so that everyone can apply this transformation easily. Here is the Haversine transformation in the gallery, ready to be cloned into your dashboard and executed. Once cloned, we only need to provide a dataset as input, the name of the latitude and longitude field, and the coordinates of the latitude and longitude reference point. Note that it is not necessary to write a flatline wrapper in WisML from scratch. Instead, you can scriptify a dataset that has been transformed with flatline manually and use the resulting WisML script as the baseline for creating a flatline wrapper. As an example, if we take our extended stock price dataset, which has our shock value, we can use the one-step scriptify dataset, which will create a WisML script that performs the very last step applied to this dataset. In this case, that is the transformation that added the shock. We now have a script that takes as input a dataset and will compute the shock of the field named price. We can see the source code for this script, and we can see the flatline transformation embedded within it. In this tutorial, we introduced Flatline, which is a domain-specific language that enables programmatic feature engineering and filtering. We also defined feature engineering and showed why it is important with a few examples. And then we explored some of the automatic transformations that BigML performs to simplify machine learning, like the partitioning of date-time fields and the bag of word analysis for text fields. Next, we looked at some of the built-in functions available in the UI for filtering and feature engineering. For example, discretization and normalization. Then we looked at how to write flatline expressions, defining the structure, and then learning how to write them through examples. And finally, we mentioned that it is possible to use WisML to wrap flatline transformations to create reusable transformations and filters. And we also saw that these flatline wrappers can be created using the one-step scriptify and then shared in the gallery.